In this episode, we are building a practical understanding of the operating system, OS, because many beginners reach cybersecurity analysis before they truly understand the layer of technology where so much suspicious activity actually becomes visible. That gap creates frustration because alerts, process behavior, account misuse, file changes, startup activity, and network connections all make more sense when you understand the OS as the environment coordinating those actions. If the OS feels like a black box, then security events often feel random, and random feeling events are hard to investigate with confidence. What helps is learning to see the OS not as a mysterious background feature that simply makes a computer turn on, but as the traffic manager, rule keeper, resource coordinator, and activity recorder that shapes how software, users, and devices interact. Once that picture becomes clear, a lot of cybersecurity language stops sounding abstract and starts sounding like a description of normal or abnormal behavior inside a system you can actually imagine. At a high level, the OS sits between hardware and software and helps them work together in an organized way. Hardware includes the physical parts of the system, such as processing components, memory, storage devices, and network interfaces, while software includes the applications and services people rely on every day. Without the OS, those pieces would not cooperate in a useful and stable way for ordinary users or administrators. The OS allocates resources, manages access, coordinates input and output, tracks files, runs applications, and provides a predictable environment so that users do not need to think directly in terms of raw electrical activity or hardware instructions. From an analyst's perspective, that matters because security events rarely happen in a vacuum. They happen inside an environment where the OS decides who can start a process, what memory can be used, what files can be touched, what network communication is allowed, and what system records are created along the way. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. One of the most important OS ideas for analysts is the concept of a process, because much of what security teams investigate involves something running that should not be running in the wrong way, or running at the wrong time. A process is simply a running instance of a program. But once a program is active, it starts consuming resources, requesting access, and interacting with the rest of the system. Analysts care about processes because they can reveal execution behavior, suspicious parent-child relationships, unusual launch locations, unexpected privileges, and patterns that suggest malware or abuse. If a seemingly ordinary application starts spawning other tools, reaching into temporary folders, or launching in ways that do not fit its normal purpose, that becomes meaningful. A beginner does not need to memorize every possible process pattern, but it helps to understand that the OS is constantly creating, tracking, and stopping these running activities, and that many endpoint clues become understandable only when you realize that the system is full of active, changing processes rather than static installed software. Memory is another core concept because a great deal of system behavior depends on what the OS places into working space while applications and services are active. Memory is where data and instructions are held temporarily so they can be used quickly, which is different from long-term storage where files rest when they are not being actively processed. From a security point of view, memory matters because malicious code, credentials, active network sessions, and process behavior may all be visible there while the system is running. The OS decides how memory is allocated, what space belongs to which process, and how one running program is kept from casually interfering with another. This management is important for both stability and security. If analysts hear that something executed only in memory, or that certain activity vanished after a reboot, that language starts making more sense once they realize that not every important sign of compromise lives neatly on disk. Some of the most valuable evidence can exist in live memory only for a limited time. Storage and the file system also deserve careful attention because analysts often investigate changes to files, locations, permissions, and execution paths. The OS organizes data into a file system so users and applications can save, find, modify, and remove information in structured ways. At first, this sounds like ordinary computer housekeeping, but it has enormous security value because files are where applications live, documents are stored, scripts are executed, and many traces of system behavior remain after an action has finished. Analysts care about where files appear, which accounts created them, how permissions are set, whether sensitive data is exposed, and whether a program is running from an unusual or temporary location. The OS also keeps track of metadata around files, which can provide useful clues during an investigation. When you understand that the file system is not just a digital filing cabinet, but also a record of where system activity leaves traces, it becomes easier to understand why defenders pay so much attention to file paths, changes, and patterns of access. Users, accounts, and privileges form another major OS concept because cybersecurity often comes down to whether the right identity had the right level of access at the right time. The OS provides the framework through which users sign in, permissions are applied, groups are assigned, and access decisions are made. This means the OS is not only managing files and programs. It is also enforcing rules about who can perform certain actions and who should be blocked from doing so. Analysts therefore pay close attention to account creation, failed sign-ins, privilege changes, unusual access times, and actions that do not fit a user's normal role. A standard user account and a highly privileged administrative account are not the same thing. An activity that is relatively harmless under one type of account can become much more dangerous under the other. For beginners, one of the most helpful habits is simply asking what account performed the action, what level of privilege it had, and whether that level of access matched the purpose the account was supposed to serve. Closely related to accounts is the idea of permission boundaries, because the OS is constantly deciding what can and cannot be done by users, processes, and services. Permissions apply to files, directories, system settings, installed software, devices, and network capabilities, and they are a major part of how an OS prevents chaos. In a healthy environment, permissions limit unnecessary access and reduce the blast radius when something goes wrong. In an unhealthy environment, overly broad permissions make compromise easier because once one account or process is abused, the attacker may gain access far beyond what was necessary. Analysts care about this because suspicious behavior often looks different when viewed through the lens of privilege. A script running in a user space may be concerning, but a script making system-wide changes with elevated rights is usually more urgent. The OS therefore becomes the layer where least privilege either lives in practice or fails in practice, and understanding that distinction helps analysts interpret the seriousness of many different kinds of activity. Services and background tasks are another area where beginners need OS familiarity, because not all important activity happens in visible applications opened by a user. Many essential system functions happen through services that start automatically, run quietly in the background, and support networking, updates, authentication, scheduling, and application behavior. That makes them useful to the system, but it also makes them interesting to attackers who want persistence, quiet execution, or privileged access. Analysts pay attention to services that appear unexpectedly, change their settings, restart at unusual times, or launch from strange locations. The same idea applies to scheduled tasks and startup items, because the OS provides several ways for programs to run automatically when the system starts or when certain conditions are met. For security work, that means one of the most important questions is not simply what ran, but how it got there and why it keeps returning. When you understand how the OS supports background activity, persistence becomes a much clearer concept instead of sounding like a vague term from a threat report. The distinction between user space and deeper system control is also important, even if you never use highly technical language for it. Some parts of the OS operate closer to the core of the system and have broad authority to manage hardware, memory, and low-level functions, while ordinary applications typically operate with more limited reach. For an analyst, this matters because activity occurring at different depths of the OS carries different implications. A normal application crashing in user space is not the same kind of event as malicious code altering deeper system behavior or interfering with protective controls. The closer suspicious activity gets to the trusted core of the OS, the more serious and harder to detect it may become. Beginners do not need to become operating system internals experts, but they do benefit from understanding that the OS is layered and that some layers carry greater authority than others. That simple idea helps explain why certain types of malicious behavior are more dangerous, more durable, and more difficult for defenders to observe directly. Networking through the OS is another major concept because even when analysts think they are investigating a network problem, much of the relevant behavior still appears through the system itself. The OS manages how the device communicates, what services listen for connections, how applications request network access, and how local settings influence communication. If a process suddenly begins reaching out to unfamiliar destinations, listening on an unexpected port, or transmitting data in a way that does not fit its role, the OSouth is the place where much of that behavior becomes visible. Analysts therefore need a basic understanding that the system is constantly translating application requests into actual network actions. This makes it easier to connect endpoint activity with network activity instead of treating them as separate universes. A suspicious login, a new process, and an outbound connection may all be part of one story. The OS is often the meeting point where those clues converge, which is why security analysis benefits so much from understanding how the local system participates in communication. Logging and event recording are central OS concepts because the system is one of the most important sources of evidence during detection and investigation. The OS can record account activity, service starts and stops, application execution, access failures, changes to settings, and many other events that help analysts reconstruct what happened over time. That does not mean every useful clue comes from the OS, but it does mean that system logs often form the backbone of endpoint visibility. Beginners sometimes think logging is a separate security topic, but it is really tied directly to OS behavior because the system decides what kinds of events can be captured, how they are labeled, and how they are made available for collection or review. This is why analysts care not only about whether an event occurred, but also whether the system recorded it in a reliable and searchable way. Good system logs can turn uncertainty into a timeline. Weak or missing system logs can leave even obvious compromise difficult to explain with confidence. Performance and resource use also matter more to analysts than many people expect, because unusual strain on the system can be a clue in its own right. The OS tracks processor use, memory consumption, disk activity, and other signs of how hard the system is working. A sudden spike in resource consumption is not automatically malicious, but it may be worth attention if it appears without a normal explanation, especially when combined with unusual processes, strange services, or suspicious connections. Analysts also need to understand that legitimate software problems can create symptoms that look scary at first glance, such as crashes, slow performance, or repeated failures. This is one reason OS awareness improves judgment. It helps defenders distinguish between system instability, administrative change, software error, and actual hostile activity. The more you understand about how the OS normally uses resources and responds under stress, the easier it becomes to decide whether an event is likely just operational noise or something that deserves escalation and deeper investigation. Another core idea is that systems change over time, and the OS is one of the main places where those changes are managed, recorded, and enforced. Updates, configuration changes, software installation, policy adjustments, driver additions, and account modifications all pass through OS structures in some way. Analysts care because change is not only normal, but also one of the easiest ways for malicious behavior to hide in plain sight. A threat actor may create a new account, alter a startup setting, add a service, disable a control, or change a network configuration, and each of those actions may look like ordinary system administration unless viewed in the right context. This means defenders need some appreciation for the difference between expected maintenance and suspicious modification. For a beginner, that does not require memorizing every administrative tool. It requires understanding that the OS is a living environment where both legitimate operators and malicious actors try to shape future behavior, and that many investigations are really efforts to separate authorized change from unauthorized change. Virtualization and abstraction also belong in this conversation because modern environments do not always map cleanly to one physical machine running one OS for one user. A single physical device may host multiple logical systems, each with its own OS, its own processes, and its own security story. Cloud workloads, virtual machines, and other abstracted environments still rely on operating system concepts even when the underlying hardware is far away from the user or analyst. This matters because beginners sometimes assume OS knowledge only belongs to traditional desktops or servers sitting in a room they can imagine. In reality, the same ideas around processes, memory, storage, logging, privileges, startup activity, and network behavior remain relevant across many different deployment models. The OS may not always be visible in the same way, but it is still the stage where much of the activity occurs. A solid analyst, therefore, carries OS thinking into physical, virtual, and cloud environments instead of assuming that those worlds are completely separate from one another. By the end of this discussion, the most important point to carry forward is that the OS is one of the main places where cybersecurity becomes observable. It manages users, permissions, files, memory, processes, services, communication, and system records, which means it sits at the center of many of the clues analysts rely on to understand what a device is doing. When you understand the OS as an active coordinator rather than a passive background feature, a huge amount of security language becomes easier to follow. Alerts start sounding like descriptions of system behavior instead of mysterious warnings from nowhere. Investigations start looking like efforts to understand how the OS was used, misused, or changed over time. That is why core OS concepts matter so much for analysts. They give structure to what would otherwise feel like scattered evidence, and they help you move from merely noticing events to actually understanding what those events mean inside a living system.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.